Yes, I'm Justin Murray. I'm from VMware's Alliances in Palo Alto, just down the road here. And my co-speaker I'd like to introduce is Ramesh Pedakotla from HP. Long-term collaboration going on between VMware and HP and actually other companies on the Java front. So what we want to do here in the next 60 minutes or so is give you what we learned over the several years we've been working together about deploying Java. I'm originally from Ireland, so I have a funny accent, and I'm used to, in small bottles, getting a lot stronger stuff than whatever this is. It's not doing me any good this morning. So we're going to talk about Java applications on vSphere. A lot of customers are moving their Java applications to vSphere. Some folks have some trip-ups. I'm going to try and keep you out of those pitfalls in this next 60 minutes. That's the purpose of this talk, is to try and give you some best practices, along with the justification of why it's good to do it now, some best practices to keep you out of some pitfalls. May I preface this part with, there's nothing special about Java workloads. The JVM is written in C++. There are tons of workloads like VoIP workloads written in C++ running on VMware today. It just so happens that Java plus SAP plus Oracle are all memory-hungry, memory-intensive processes. They love to have huge memory, like 2 gigabytes or 4 gigabytes. I have one customer that has an 8 gigabyte Java heap. It's running fine on VMware. They've tuned the heck out of the garbage collector, but that's nothing to do with VMware. So most of your applications, I would hazard a guess that over 90% of your applications in Java will virtualize fine if you stick to these principles we're going to give you here. And I know some of you in the audience have probably run into speed bumps with Java. We'll talk about those in the question and answer session later on. Please hold the questions till the end so as we can get through a fair amount of material here. And this is a technical session. There's little or no marketing in this presentation. It's quite technical. How many people here are familiar with Java? Wonderful. You're my buddies. How many people here are familiar with Java on VMware? About 50, 60%. This is very, very good and very encouraging. Thank you. So I'll spend 40 to 45 minutes talking about the best practices. Ramesh will then join me and talk about his work in measuring Java on VMware. And this has been going on for the 3.5 years that I've been at VMware, and had been going on for 1.5 years or 2 before that. So there are actually 3 or 4 reports now describing various testing that's been going on for Java on VMware. I'm not allowed to say anything bad here, and I'll try not to say anything bad, but, you know, Irish people, we say bad things sometimes. So, why do it now? It will be the first topic. That'll be fast and furious. I think most of us are persuaded that we should do Java on VMware, or at least try it right now. The number of Java applications that don't fit on VMware is a rapidly diminishing list, in my opinion. I spend most of my time, probably 3 or 4 phone calls a week, delivering this material and other material to customers to say, here's how to go forward with your Java stuff on VMware. And to summarize it very briefly, take your Java application, transport it without change, no source code changes, no command line changes, no heap size changes, into a VM on its own, into a virtual machine on its own. If possible, I would suggest that if it's a big thing like a WebSphere or WebLogic, don't P2V it, reinstall it into a clean VM, just to get a completely clean environment. Put that isolated VM on an isolated ESX box and drive traffic through it like crazy. Put load runner on it, drive a lot of traffic through it, and judge for yourself what the effect of a Java application in an ideal environment on VMware looks like. Isolated from everything else, alone in the VM, and alone on the ESX box. And then start moving other things either into the VM or into the ESX server. Do it in a stepwise fashion, like that. So that's a summary of my advice here. I'll talk about something like 6 best practices. They're easy stuff for deployment of Java on ESX. The main one is memory. Get memory right, and 70% or 80% of your problems go away. Java is memory hungry. Oracle is memory hungry. SAP is memory hungry. We can handle them all on VMware now. We've done a lot of work over the past couple of years on that. The performance test experiences at HB will be Ramesh's piece. How will it perform? How many people here are concerned about Java performance? How many people here are concerned about Java performance on VMware? No need to be. It's actually quite close to physical. If you've got a very badly performing Java application on physical, it'll perform the same way on virtual. We don't improve it for you. Although Ramesh will show you a figure of a Java application based on WebSphere, it's the day trader application, running 4% better on virtual than physical. It is possible to beat physical, which to me is astonishing. To you it should be astonishing. Wait for Ramesh's graphs to see that. And the call to action is, if you're not planning to virtualize your Java applications or middleware today, you should be thinking about it. There's a big wave going on. We're being kept very, very busy talking to Java people about virtualizing. So why do it now? We think it's an ideal candidate for virtualization because it's undergone extensive testing over the last 4 years. And each year, it's gotten better and better. We had something like a 10 to 20% overhead a couple of years ago. It's down beneath 10% now for many applications. It's down to 5% or less for some applications. So you need to test yours to find out where yours is on that graph. Somewhere in the 10-15% is expected. Higher than that, we would look and say, is there anything we've missed in the tuning and configuration? The performance of middleware-based systems, I mean WebSphere, WebLogic, JBoss, Tomcat. How many people here have WebSphere? About 30%. How many people here have WebLogic? About 30%. It's the market share, isn't it? And JBoss or Tomcat? About the remaining people. Some overlapping folks. So you can virtualize all of those. An application written for WebSphere, application written for WebLogic, no reason you shouldn't think about virtualizing those. We think middleware is going to be one of the first applications in the cloud, and that's been the theme here this week, the cloud, move to the cloud. The people who are going to put applications into the cloud first are going to be developers. They're probably developing in Java. There are 3 million Java developers in the world. It's the mainstream language now. The thing that's going to go into the cloud first is a Java middleware. That's the thing you need to test first on virtualization, in our opinion. Why are they a good fit together? Well, the motherhood and apple pie, isolation, consolidation, and rapid provisioning. Hardware vendors now are building devices that send virtual machines from that device to ESX servers in template form or in virtual machine form and back again. So there are now hardware vendors building virtualization-specific devices. And not small hardware vendors either, large ones. So this says that rapid provisioning is a serious benefit from virtualizing your Java. I'd like you to think about isolation for a second. Isolation is a benefit in that you can see what the performance of one virtual machine is from another. If you have more than one JVM operating in that virtual machine, it becomes a little more difficult to see which of the JVMs is causing the performance to be consumed, or whatever is going on there. I'm going to advocate here, and you'll take issue with me, I know you will, that one JVM per virtual machine is a good idea. I spoke to a person at our equivalent of this talk yesterday who has 100 JVMs in their virtual machine. I've met customers who've 30 JVMs, 40 JVMs in their virtual machine. There's nothing wrong with that. You can do it if you size the virtual machine correctly. My recommendation number 2 to you, the first one was isolate your Java into VM of its own. Recommendation number 2, keep the number of JVMs within a virtual machine down in number. Less than half a dozen. 1, if you can get there, is the perfect nirvana ideal situation. Because then you can tell a lot about the JVM and its effect on the virtual machine, its effect on the ESX server through VMware's management tools. You can look at the management tools in VMware and see exactly what that JVM is doing. So that's going to be a best practice later on. It's actually a technique which makes use of isolation as well as gaining benefits from that isolation. So now, getting into the serious technical stuff here, what are the best practices for deploying Java on VMware, on ESX? And we're deploying this on ESX 4.0 and higher now. virtual machine memory is the first choice you get when you deploy Java in a virtual machine. How big is the memory? Should the virtual machine be equal to the heap size? If it should be bigger, how much bigger? That question will be dealt with first. How many virtual CPUs am I going to give? Is it one virtual CPU, two virtual CPUs? How do I measure that? Let's look into that. My disk I/O and network I/O is something I worry about on physical systems. I also want to worry about that on virtual systems. Timekeeping is something we all pay attention to in virtualization because we can think of our virtual machines as like processes on an operating system. Sometimes they're scheduled, sometimes they're not scheduled. And when they're not scheduled, timekeeping interrupts are not arriving. So we have to treat timekeeping specially on virtual. And monitoring and management, I'll say a little bit about. And then application server-specific items, you don't need to change anything about your tuning of your application server or your tuning of your Java for VMware, for virtualization. You don't need to change your heap size. How many people here set their minimum heap size to their maximum heap size, the same value? A small number of people. Yeah. Well, that's almost a piece of folklore in the Java industry that that's a good idea. It's been around for a long time. I've talked to people inside VMware who actually wrote the garbage collector on the Sun JVM. It's optional whether you set max size to min size, and it's further optional when you do it on VMware. You don't need to make a new garbage collection strategy just because you're virtualizing. So that's the good news. Let's tackle memory very quickly here. This is a picture of an ESX server with two virtual machines on it, and we'll return to this two virtual machine image in a minute. First of all, let me give you some motivations that ESX has. You can take photographs if you like, but I'm much prettier than the picture. All of this will be in a white paper that I'll give you at the end. You don't need to write notes on it. Feel free to photograph it if you want to. The Java heap, of course, is the area that everybody pays attention to in Java. Developers, people deploying it like yourselves, you've been given a Java application by the development team and told, put that live in the data center. The data center is now virtual. Everything's virtual in the data center. The Java folks have never touched virtual before. We as a community have got to persuade them that virtualizing Java is okay. It'll be okay. And to do that, we need to protect that Java heap. So in the same way on physical systems that you keep the Java heap in physical memory as much as possible, same principle applies on virtual. Keep enough physical memory around so that your Java heap is in physical memory at all times, and Java will be happy. And I'll show you how to do that. We'll delve into that Java heap a little bit just to confirm with you how busy this Java heap is. It's a very heavy memory management area, and we'll look into it a second. But before we do, look on the left-hand side there. The Java process needs a little bit more memory than the Java heap. We typically say 1 gigabyte, 1.6 gigabytes, 2 gigabytes Java heap. But we forget about the 500 classes that Java has loaded when you started up Java. Where is that going? What about the permanent space, which is somewhat outside the Java heap? For every method that you invoke, that method goes on a stack. That stack occupies memory. All of that memory that I've just described is on the left-hand side. So in the white paper that we're going to give you, there's a formula for calculating how much memory you need there, multiplying the stack size by the number of threads, and you get a rough figure for that. Guideline number 1 is make your virtual machine memory, you see it in the arrow there beneath the virtual machine, make your virtual machine memory, when you configure your VM, bigger than your Java heap. How much bigger? Well, it depends on how many processes you're going to run alongside Java. You're going to run a management agent. You're going to run an antivirus piece of software, all in the same virtual machine. All of those need memory. So be careful about monitoring the active memory of your Java process when it's under load. How much active memory is really being used? And we find very frequently that the Java heap, although you've specified 2 gigabytes for it, the active memory is less. Now, we'll show you techniques for measuring that in a second. But looking inside that Java heap, it has 2 main areas. The Eden area, or new object area on the left-hand side, and there are sub-areas, we won't delve into those. And the old area, this is objects kept around for a long time. Studies done on Java show that objects die off very quickly. They come into being, a session object for your shopping cart. You shop around for a few minutes or seconds, and then you buy, and your session object goes away. Very few objects, well, a smaller number of objects live on for a long, long period of time. Let's look at the lifetime of a Java process for 1 minute or 2 minutes here. So in the lifetime, a new object is created always in the Java heap. All new objects go there, unless you create an object of 2 megabytes or 10 megabytes in size. That goes into the old area typically, which is a bigger area. And the difference between new and old is the algorithm used for garbage collection. The algorithm used for garbage collection in the new area is a very fast algorithm. The algorithm used for the old area is slightly slower, more oriented towards compaction of the space there. We're not going to delve into this in too detail. We're just going to see objects being created, and suddenly Eden is now full. The nursery is full. Lots of babies. Well, it's time now for the first minor garbage collection. And garbage collection, as you know, is one of the principal performance affecting things in Java. Lots of people pay attention to this. A minor garbage collection is no big deal. It takes less than 1/10 of a second. You can see them happening once every second. It's not a problem. Let the garbage collector do its work. It cleans up the area, and there are some survivors. These are objects which are still needed beyond the garbage collection. We keep building new objects, and we fill the Eden area again. Time for the second scavenge garbage collection. This is happening all the time in Java, and the amount of pause time that's caused by this garbage collection is usually insignificant. It's less than 1/10 of a second or thereabouts. In fact, if it grows anywhere close to a second, you want to look at it. Something is misconfigured. Not at the VM level, at the Java level. So our second garbage collection causes some more survivors. Now we have 3 survivors. And we keep doing that until those survivors have survived many, many garbage collections, 32. It's a changeable parameter. And these objects are now old objects. They've been around for a while. This is all quite natural in the lifetime of the process. And gradually we collect more and more old objects until we fill the old area. We've completely filled the heap in some ways now. And this is time for a major garbage collection. A major garbage collection is slower and has more area to cover than a minor or scavenge garbage collection. There are at least 10 different algorithms for this, but in general, you're going to get a full garbage collection sometime in the lifetime of your Java process, and it's going to cause some pause in the progress of the application. Now, my lesson from all this is that the ESX hypervisor is 2 floors down from here, right? The ESX hypervisor is down in the engine room, managing memory, and the guest operating system, Linux or Windows, that Java is running in, is on the next floor up, and Java is up here on the 3rd floor, or 2nd floor if you're in the US, right? So, this is unknown to the ESX hypervisor. I'm going to show you a picture of what the ESX hypervisor is seeing underneath this next. And so, nothing wrong with a full garbage collection unless it takes too much time. And that's something for your Java developers to cater for. Nothing to do with virtualization. So, this is a very busy area, as you've seen. We've seen about 2 minutes lifetime here, maybe 3 minutes lifetime. It's very busy. Lots of objects being moved around, objects being contracted, compacted, objects being deleted, new objects being created. Extremely busy area. Once we've set the system up such that all of this is being done in physical memory, Java will be happy. So how do we do that? Here are the 2 virtual machines as viewed from a hypervisor perspective. Think of the hypervisor as down here in the engine room. And it is not seeing the Java process. The guest operating system is seeing the Java process, and Java is up at the top layer, the colorful boxes at the top layer. That's the guest virtual memory. Every process on every operating system that I've dealt with operates with virtual memory. And so these are the pages of the heap at the top. They're the pages that the operating system is dealing with in the middle, and they're the pages that the hypervisor is dealing with at the bottom. This, by the way, I stole from the Resource Management Guide, which is a document on VMware's website. Very good document, Resource Management Guide. 2 levels of mapping. The guest operating system is mapping the top layer to the middle, and then the hypervisor is mapping the middle layer to the bottom. The hypervisor is in charge of the physical memory, really. It's in charge of the actual memory on the machine. And that type of mapping between guest physical memory and machine memory is being done in hardware today. It's being done by the Intel Nehalem chips with virtualization assist. That's what VT is. It's being done by the AMD Shanghai and Barcelona chips, which is what rapid virtualization indexing, or RVI, is. So this is not quite a best practice for Java, but a recommendation all the same. If you can get onto those modern hardware-assisted virtualization chips, Intel Nehalem, AMD Shanghai, AMD RVI technology, then all of this mapping here between guest physical and machine memory is actually being done in hardware, not in the hypervisor anymore, which relieves the hypervisor of a huge amount of work to do with memory mapping. Memory mapping is a large portion of our code from pre-RVI, pre-VT. So if you can move your Java systems or deploy your Java systems on Intel Nehalem, which you'll see in Ramesh's presentation, or AMD Shanghai equivalents, that's going to give you a performance boost. Purely a hardware performance boost. Sometimes a dramatic boost, actually. Sometimes 20% or better. Secondly, you'll notice that page B in the virtual machine on number 1 and page B in virtual machine number 2, when ESX comes to store a virtual machine in physical memory, a page in physical memory, it's only storing one page. That's because there's a scanning algorithm inside ESX that's looking at these guest physical memory pages and saying, page B is a page of zeros, or it's a page of certain values. And page B in virtual machine 1 has identical values. So there's no need for the hypervisor to store two pages until one of those virtual machines writes to their page. Instead, the hypervisor stores one page B, and then it does a copy on write when one of the virtual machines chooses to write to that page and change its contents. That type of thing is called transparent page sharing. It's on by default in ESX. There's no problem with doing Java here. This is the technique we use for pushing more virtual machines into limited space than will actually fit. In other words, we actually overcommit memory in ESX, something that not other hypervisors do. Well, I'm going to protect Java against that effect here, and I'm going to do it in two ways. Firstly, instead of using smaller memory pages for Java at the guest OS level, we're going to tell the guest OS to use larger pages. And we're also going to tell Java at the top of this, use large memory pages. Use 4 megabyte or 2 megabyte pages instead of 4K pages or 8K pages. And that will give you a performance boost of 5% to 20%, depending on your application. The negative effect of it, however, is that this page sharing algorithm is not quite as efficient. In fact, page sharing is almost switched off completely when you use these large pages. So you pay a price for using large pages, which is a JVM level switch and an operating system level switch. You pay the price that you may have less memory consolidation. Your memory is being used in larger pages now, and you may fit less into the memory. In fact, I would recommend to you, do not overcommit your memory. If you're filling the machine with Java, every virtual machine that you're running has Java on it, and you're running those Java processes through a lot of load. They're working very hard. As you saw there, Java needs the entire heap available to it all the time when it's working hard. So when it's working hard, the Java heap is needed. We want to keep it in physical memory. Do not overcommit the physical memory, because there is a chance you could get into a swapping situation there. So one of my customers did a massive P2V exercise where they took 200 virtual machines and moved it over from physical to virtual at once. And of course, Java got into a memory overcommitted situation. The machine was very busy. Java is working very hard at the same time, using all of its heap. Memory overcommitment causes effects that I'm going to show you, and therefore Java behaved a little worse than it should have. The instant you take the memory overcommitment away, Java behaves fine. So the motivation in ESX is to conserve and share memory. The motivation in Java is to use it as much as possible, right? These are opposite motivations. So now we're going to set some steps in place to take care of that. Here's what ESX does when memory is running short. that orange deflated balloon at the top is inside your guest operating system. It's inside Linux or inside Windows. You put it there when you install VMware tools in your guest OS. And I strongly recommend you do install VMware tools and keep it up to date. When you install VMware tools, it's possible that the ESX hypervisor, if it's running very low on physical memory, less than 15% free or thereabouts, it will ask one of the virtual machines to inflate the balloon. Inflating the balloon is just a process that started. It's really a driver, but you can think of it as a process that started that says, I need lots of memory right now. I need 5 megabytes right now of memory. And so that's what the inflation effect is. And it pins those pages in memory and hands them back to the hypervisor. Of course, this causes other processes inside the guest operating system to possibly lose memory, and therefore they might start swapping. They might be swapping at the guest OS level. Swapping Java at the guest OS level, we don't want to do. So although I'm going to tell you, keep the VMware tools installed and up to date and current, and keep the balloon driver active, if you were to see the balloon driver taking effects, in other words, doing some work inside your virtual machine, you should look at it. We want to protect Java from that balloon driver effects. And I'll say how to do that in a few seconds. Lastly, and this is really if the balloon driver is not able to get back some memory stolen away from another VM, if that happens, then ESX will start to swap virtual machines, just as physical systems will swap a process on a physical box. ESX will now begin to swap a virtual machine out to the swap file on the disk. Notice I say it'll swap the virtual machine's unreserved memory space. We're going to prevent the swapping from happening and prevent the ballooning from happening in the next slide. So, step number 1 for memory, and I said memory is the most important area for best practices in Java, is size your virtual machine's memory to leave adequate space for the Java heap, and you may have 2 Java processes, so you've got to add those heaps together. Leave enough space for the JVM code. There is a formula for that in the paper. Any other concurrently executing process, like a management process or an antivirus process or a scanner process of some kind, calculate all the memory space you need, and then leave some overhead space for Linux or Windows as well. About maybe half a gigabyte for Linux, maybe a little more for Windows. Some space for the memory to keep its buffers in as well. So when I did my testing of WebLogic, as it turned out, I used a 1.6 gigabyte heap for the Java process. My virtual machine memory was configured at 2.2 gigabytes. 0.6 of a gigabyte left over as overhead space. What you don't want to see is swapping at the guest OS level, swapping at the Linux or Windows level. If you see that swapping, you've misconfigured your virtual machine. It's too small. And be careful to configure enough swap space as well so that you can start all your processes on that virtual machine. Second recommendation is set a memory reservation. This is something in ESX now, in Virtual Center. Set a memory reservation in the Virtual Center client to the size of active memory for their virtual machines. Who here who deals with virtual machines every day understands the active memory of that virtual machine and can tell me the number? A small number of people, right? It's a task that I'm giving you to do here. So I'm going to take away that task and say, whatever the configured memory is of that virtual machine, you could set the reservation to that level, and you're safe. You're safe even if the virtual machine were to move from host A, ESX host A, to ESX host B, and it turns out ESX host B is very tight on memory. The reservation will protect that. There is some waste, though, in using the configured memory approach. The wastage is if the JVM is not actually using all that heap, or if the virtual machine is way, way bigger than the JVM code. I had one situation where a customer configured the virtual machine to have 8 gigabytes, and the one Java process in there was 1 gigabyte heap. That's way too big. That would be very wasteful of memory there. So if you're good at measuring the active memory under load, under spike load of your JVM, then find that number and set the reservation for that virtual machine to that active memory level. That's the absolutely correct an absolutely no waste approach to configuring memory. A slightly more wasteful approach, but a much easier one, is to set the reservation to the configured memory. In other words, what you built the virtual machine to be in the first place. In my example, my configured memory would be 2.2 gigabytes. My active memory would be 1.7, 1.6 gigabytes for my JVM. So I think most folks will fit into the if in doubt case. If in doubt. It's slightly wasteful of memory, but not tremendously so. Use large memory pages. This is a JVM setting minus XLP. You'll see it on all of the IBM benchmarks as minus XLP. Large pages. You're telling Java, use large memory pages for the top layer of memory that I showed you in the three-layer cake. Use a switch at the OS level also. It's huge mem. Huge mem is the switch on Linux. And that's also documented in the paper. And then use the VMware Distributed Resource Scheduler to balance your load. Somebody asked me in this talk yesterday, if I have a cluster of ESX servers, where would you suggest I cluster my Java processes? Should I spread them out across the ESX servers, or should I put them all on one not very busy box? There are motivations for doing both, actually. You know, should I condense all my Java into one ESX server, or should I spread it out across the cluster? DRS will make that decision for you. You don't need to do it manually. So this is how to set a reservation in the vCenter client. The second line from the top there says, I'm setting this reservation to be 2.48 megabytes or 2.4 gigabytes for this virtual machine. You can do this in scripted form using Power CLI, or you can do it interactively. People who have hundreds of virtual machines prefer to script this. So now let's move on. Topic number 2 is about Java threads. That was memory. Memory is extremely important. You should be spending about 70% of your time in setting up your virtual machines on the memory topic if they're going to run intensive Java processes. And the classic situation that I see is with our customers is they pile on the JVMs onto the ESX server. They start with one virtual machine, 2 virtual machines, 3 virtual machines, and we pile on the virtual machines onto that ESX server. As long as you don't overcommit memory, you're going to be safe. And one technique for not overcommitting memory is to set a reservation, as I've indicated. Another technique is to get a promise from your VI admins, a verbal promise. We will never overcommit memory here. If you have that promise and if people stick to it, then you don't need the reservation. The reservation is a cast iron guarantee, really. So Java threads execute on one virtual CPU at any one time. That's done by the guest OS. The guest OS is entirely in control of that. And a virtual CPU, which we're in control of in ESX, executes on only one physical CPU at any one time. You can see that more clearly here. The physical CPUs are on the right-hand side. The virtual CPUs are in the middle. They're inside the virtual machine, or actually inside the virtual machine monitor, which is around the virtual machine. And then a bunch of threads are running inside one JVM process in that virtual machine. Now this is a somewhat contradictory picture. Most Java processes that we look at have many, many fewer threads in the running state than they have in the ready-to-run or waiting state. If you were to do a kill -3 on your Java process, it doesn't kill it, by the way. If you do a kill -3 on the PID of your Java process, it will dump out the thread states for you. It's a standard technique in debugging thread locking and thread contention. When you look at those threads, you'll see 50 to 100 threads that are actually sleeping or waiting. They're waiting for something to happen on the socket, or they're waiting for some other thread to release a lock. Only half a dozen or less threads are really running or ready to run. We don't actually write very well-threaded Java programs at all, although we think we do. There's not a need for 32 concurrent threads very often in Java. So those threads in red are being multiplexed by the guest operating system onto the vCPUs. Remember, the guest operating system doesn't know these are not physical CPUs. It says, oh, these are my physical CPUs. I'm going to run threads on them. I'm going to multiplex the threads across them. And then ESX is taking the virtual CPUs and multiplexing those onto the physical ones, one at a time. It's not necessary for all of those vCPUs to be ready to run for any one of them to make progress. They don't have to wait in total sync with each other. vCPU 0 can execute for a while, even if the rest of the vCPUs are not ready to run. That used to be a lot more strict in previous versions of ESX. It's now not strict at all. Now, how many virtual CPUs are ideal for my Java application? I'm going to role play a customer here, and you're going to role play Justin and Ramesh. How many vCPUs are appropriate for my application? I've told you nothing about the application, but you should be able to tell me the answer. It depends. There's a consultant in the room. It absolutely does depend on your application and what the thread profile of that application is. The only way you're going to find out is to run some tests on the application with 1 virtual CPU, 2 virtual CPUs, and 4. And that sounds like a lot of work to give you, so I'm going to give you the answer. Start with 2. And the reason I say that is because Ramesh's data from his measurement and other data measurements seem to indicate that 2 to 4 virtual CPUs are a sweet spot for Java today. 4 years ago, with ESX 2.0, 2.5, 1 virtual CPU was the sweet spot. Today, it's 2 or 4. So start with 2 and work upwards to 4 if you've got the luxury of time to do some testing. That's for 1 JVM in the virtual machine. If you've got 2 JVMs in the virtual machine, the story will be different if they're running together. So use the lowest number of virtual CPUs that is practical for your application. Why? Don't you give me 8 virtual CPUs nowadays? Aren't you promising 16 virtual CPUs next year or sometime in the future? Yes, we are going to do that, but it's not the case that more virtual CPUs is always better for your Java process. In fact, a lot of Java processes will run fine on 1. The majority, as I've indicated, of our testing shows that 2 virtual CPUs to 4 are the sweet spots for Java nowadays. The lower number is really to take some of the load off the hypervisor. What is that load? It's the interrupt handling that every virtual CPU has to simulate. Physical CPUs get interrupts, therefore virtual CPUs must get interrupts too, because they're simulating what's going on in the physical level. A hardware interrupt, like a timer interrupt, has to be handled by the virtual CPU. Every one of those interrupts is stopping your process from running, stopping your Java process from running. The fewer the number of virtual CPUs, the fewer the number of interrupts are arriving, the less work ESX is doing, the more it's getting out of your way. ESX is doing its level best to get your user code to run directly on the hardware and not get in the way. But one point at which it does get in the way is interrupt handling. It has to do that because those are privileged instructions. So using a lower number of virtual CPUs will gain you some benefits most of the time. One exception, and this is a corner case, is if you're using multi-threaded GC. I don't advocate that you use that. Most GC is already multi-threaded today. And you specify the number of threads. This is not advocating this option, but if you are using this option, make the number of virtual CPUs equal to the number of threads for GC, because when GC does run in parallel, garbage collector runs in parallel, it will start 4 threads to do so, and there aren't enough vCPUs to run the 4 in parallel. So that's the one corner case where we can be absolutely categorical and say 4 virtual CPUs are appropriate there. Now moving to lighter weight topics. The 2 topics so far have been memory, threads, and virtual CPUs. Those are 80% of the issues you'll come across, or the things you should focus on. The next is the 20% that you should do on physical systems as well as virtual. Check your disk latencies. The D average, G average, and K average are the device latency, the kernel latency, ESX latency. That should be 0 or very close. And the guest average, the amount of time is being spent inside the guest OS on any one disk I/O. You can see this using vCenter, or you can also see it using ESX Top or remote ESX Top, which are internal tools that you can get in the console OS or get in the remote management agent, VMA, Virtual Infrastructure Management Agent. I'd advise system admins and VI admins that are spending a lot of time with deploying Java, get to know this tool. It's very powerful, very useful to you, ESX Top or now remote ESX Top. Make sure your guest OS is not swapping, and you would do that by using guest OS tools like vmstat, iostat, and SAR. You can see the swapping in those. You should have enough swap space configured in your guest because some operating systems require you to have enough swap space to start a process on the assumption that it might swap someday. You do not want to see guest OS swapping at all with Java processes. And by the way, all of this talk is about production Java or staging Java under heavy load. I'm not really talking about developer Java where we can tolerate some delays sometimes. This is about the real stuff now, going live with real processes. Okay. Disk I/O. This is ESX top in interactive mode. If you were debugging some issue, you probably wouldn't run ESX top in interactive mode. You'd run ESX top in batch mode, ESX top -b, collect the data, and there's a very nice tool on a website called vpivot.com. vpivot.com. The tool is called vplot. It was written by one of our support engineers in his spare time. We have guys like this. And he wrote this to take this data and plot it in a friendly fashion. The tool is vplot, and the website is vpivot.com. Network I/O is a little more of a sensitive area for Java. Java tends not to be disk I/O intensive unless you're doing a lot of logging, and one way to speed Java up is to take the logging level down. In other words, don't do so much error logging. Or to remove the exception handling, to fix the exceptions, so that you're not spilling the entire Java stack out to the I/O every time you get an exception. That's a notorious performance area for Java. No different on virtual. If you've got a lot of exceptions on physical, you'll get the same exceptions on virtual. We don't cure that problem for you. Look on the network to see what your packet receive rates and packet send rates are, and whether there are any dropped packets. Dropped packets might be the result of not the correct negotiation between your switch and your network card. They might be on full duplex, half duplex, set up wrong. If you've got dropped packets, you've got a network configuration issue, nothing to do with Java. It needs to be fixed for Java to operate perfectly. Here's ESX top output showing me the speed of the card on the left-hand side, 1,000 gig or gig E on the left-hand side, and the performance in terms of packets per second on the right. You can also see this data in Virtual Center. I just decided to use ESX top here just as to show you what it looks like. Timekeeping in virtual machines is important, and especially important for Java because Java is sensitive to timestamps, especially in the lightweight third-party authentication area, in the security area. It's required in certain cases for the timestamp on one end of a socket to be within a certain tolerance of the timestamp on the other end of that socket. That's just one example of where Java and timekeeping are important. And timekeeping is important by definition on virtual systems because we think of ESX as the operating system, think of the virtual machines as the processes. Whenever the process is descheduled, the clock is stopped. There's no timer interrupts coming. Whenever the VM gets rescheduled by ESX, timer interrupts are arriving again, and we've got to catch up with real time. And we've got whole engineering sections dedicated to taking care of that, and it is in good shape. But we need your help on this. Synchronize the time on the ESX host with an NTP source is the recommendation. These recommendations came from our time lords, not from me. Thank you for the Star Trek analogy there. Synchronize the time in your virtual machine with the guest inside the guest operating system with an NTP source for Linux or using a tool called W32 time for Windows. If you've done those two things, you've done the 90% that you need to do for timekeeping, right? You can get some benefit by using more modern Linux kernels, SLES 10 Service Pack 2, that's SUSE Linux 10 Service Pack 2, or SUSE Linux 11 and above. Those have been changed as a result of VMware R&D guys going to the Linux community and saying, you could be interrupting the clock at a far fewer rate of time than you are doing now, or sending timer interrupts in a far fewer fashion. Instead of 1,000 times a second, send interrupts at 100 times a second. Now ESX has to do less work, and now the thing goes faster. So these are virtualization-friendly Linux kernels, and I'm going to show you what they are in a few minutes. If you happen to be using the Sun Hotspot JVM and Windows combined together, there's an option there called Force Time High Resolution, which you will see in some of the benchmarking parameters like spec.org. It actually forces the time resolution to be lower, and it actually helps you, we found, when we tested. Uses few virtual CPUs as are right for your application. If 2 CPUs seem to be giving you the right response time and transactions per second, then that's a great number. If 4 gives you an order of magnitude better, that's a great number. Avoid using /PM timer. We found some problems with symmetric multiprocessing HALs there. So avoid using /PM timer on Windows guest operating systems in the boot.ini file. Here are the kernels that are ideal for you to use, particularly if you're using Linux. And the vast majority of folks who call us at VMware using Java on VMware are using Linux. The vast majority of the benchmarks are also done on Linux. I won't say anything about that other than I like Linux myself as well. On ESX 3.5, SLES 10 Service Pack 2, Red Hat 5.4. On ESX 4.x, that's 4.0 and 4.1, SLES 11, Ubuntu 9.04, and Ubuntu 9.10 would be good choices. And SLES 10 Service Pack 3 works just as well. Just getting into the final sections of my part here now, it's often the question that arrives to us, what is the benchmark I should be using for testing my system with Java on VMware? And we'll show you some benchmark figures here that prove the point that Java can run fine on VMware. But there isn't any ideal benchmark that we see. SpecJBB isn't ideal. SpecJ App Server, slightly better. SpecJ Enterprise 2010, we're going to do some further investigations with our colleagues and partners on that. But the best benchmark of all is your real application under load. If you can set it up in your staging area, your pre-production area, in a virtual machine with a load driver that drives load through your application, your actual application code, that is the best way to go, in our opinion, for that. For easier monitoring and load balancing, use 1 JVM process per virtual machine. This statement has been the bane of my life for the past year because every customer says, I'm not going to do that. I have to pay licenses for every guest operating system. I don't want to pay 100 licenses for 100 JVMs. And I'm okay with it. This is a very loose recommendation. It does have some benefits, though. And by no means is this the golden rule that you have to stick to. It's simply a fairly light recommendation. The benefits you get from having a fewer number of JVMs per virtual machine are that the VMware tools become immediately pertinent to your Java data. Whatever the virtual machine is doing is what Java is doing. If you've got 100 JVMs or 20 JVMs running concurrently in your virtual machine, it's very difficult to see from the VMware tools which JVM is the culprit inside that guest OS for anything that might be happening. That's the main benefit of that. And we've done some advanced thinking around making the guest OS just a very, very thin wrapper around the JVM. That's not there yet, but someday. JVM garbage collection strategy. Should I be using concurrent mark sweep? Should I be using parallel GC? There's a whole bunch of exotic strategies around garbage collection. You don't need to change your strategy when you go to virtual. That's the good news. You don't need to change a single line of Java code when you go to virtual. You don't need to change your thread pool sizing or your JDBC connection sizing. One side point here is that while virtualizing your Java systems, you might talk to your architects and say, have you considered bringing your heap size down? You know, it's okay for the garbage collector to do its work. We don't have to have zero garbage collection going on. Garbage collection should be kicking in once every couple of seconds and doing some work, provided the pauses that it's causing, if it's causing any, are not unacceptable. And so tune down your Java heap, less memory to manage, more JVMs on the ESX server, right? The smaller your heap, the smaller your virtual machine size, the more you can fit into the ESX server. So try not to have an 8 gigabyte heap if your actual active working set is 1 gigabyte of objects. That's wasteful. That's not really virtualization, that's good Java tuning anyway. Tune in the same way as you would on physical implementations. And by the way, when you're doing a comparison with your older physical systems, taking a 16-way large Unix machine and comparing it with a 2 virtual CPU VM is not a fair comparison. You know, Java is in a more constrained environment on 2 virtual CPUs than it is on 16 physical ones. The correct comparison there that Ramesh is going to show you is a 2 physical JVM running against a 2 virtual CPU JVM. That's the correct comparison to make. So those are the best practices. I'm going to hand over to Ramesh as soon as I've said, how do you get started? How do you get prepared? One of the ways you get prepared is to run Capacity Planner, which is a long-lived tool running on your physical systems that looks at your physical systems and says, here are some ideal candidates for virtualization, and here are some not-so-ideal candidates. What are the not-so-ideal candidates? The Java processes that cause 10,000 context switches per second, because they're forking a process every tenth of a second, are not the perfect candidates. Context switches causes some overhead on ESX. So look at your context switches. Very few of you will have Java applications that fork a process, that cause a new process. The methodology in Java is to create a new thread, which is a lightweight thing. That's not the context switches I'm talking about here. I'm talking about starting a new whole process from a Java system. We've seen some of those with older application servers, and that type of thing, 10,000 context switches per second, is going to be slow. There are 5% or so of Java applications that will run slowly always, on physical and the virtual. Disk I/O, make sure your memory consumption's okay. Once you've handled memory and threads and virtual CPUs, you've set Java up for success. Use the latest versions of ESX and vSphere, and as I mentioned before, use hardware virtualization techniques because it's built into the chips now, the latest chips, and it helps the ESX hypervisor to handle that memory mapping that it's got to do between the virtual machine and the physical machines at the bottom. All of this is in the best practices guide, which you'll see at the end of Ramesh's presentation. Now, he's going to talk about some real measurements that back up the data I've been giving you.
Hi, I'm Ramesh, and I work at HP. I'll be showing 2 data points here. The first one is a performance-oriented workload, and the second workload is showing a load balancing and availability features. This is the test configuration where we have run some physical to virtual comparison benchmark using vSphere on identical systems with ESX4 installed on one server and Red Hat, the same operating system, on the other. And this is an 8-core Nehalem server, and the data shows that in 2 and 4-core single instance comparisons, the virtual configuration gives you a better performance because of the hardware features, the VT, Intel VT technology that assists hypervisor, thus improving the performance in the virtualized environment. And the ESX is also NUMA aware, and that also helps in the performance. And in this case, we are comparing with a single CPU virtual to single CPU physical in 1 core, and comparing with all the cores that are on the machine. The next slide will show this is a 2 virtual CPU or 2 core comparison with single virtual machine, 2 and 4 virtual machines in this case. Also, you can see that there is a performance improvement of 4 to 6% in 1 virtual machine and 2 virtual machine cases. And with 4 virtual machines running on the server, you will see a 10% to 15% degradation because of the VMs running on multiple physical CPUs. So there is a slight overhead over when you hop from one processor to another. And in the next slide, this shows you a 4 virtual CPU configuration, virtual and physical CPU configuration comparisons. And in this case, you will see a 3% improvement even if you are running on 2 physical CPUs, because ESX is new malware and it's able to run Java on a quad-core single physical CPU. So there is an advantage when running on a physical environment. The next configuration, in this configuration, what we are showing is a load balancing across multiple ESX servers and how you can improve the performance and response time when running on multiple ESX servers. The ESX server, this is an 8-core Nehalem processor, the same system, with 2 virtual CPU VMs and 4 VMs running on each box. And we are running 2 virtual two ESX servers, and we'll show the performance comparisons when running on multiple ESX servers. In this chart, with 1 CPU, 1 virtual machine, you are running the virtual machine on 1 ESX server, and with 2 virtual machines, you are running 2 virtual machines, 1 virtual machine on 1 ESX server, and the other virtual machine is running on another ESX server. In this case, you will see that as you increase the number of virtual machines, you will see a better performance, better response time, and also the CPU utilization comes down as you add multiple VMs and running on multiple ESX server. And in this case, the load is constant in this case, and with 1 virtual machine, you will see that with 2 virtual machines, you will see higher performance, more than double the performance, because in a single virtual machine environment, there is a lot more constraint and a lot more overhead when handling the load in that case. So it's better to go with multiple virtual machines when you cannot handle the load with 1 virtual machine. And this chart shows you the response time comparison between the virtual and physical environment. And you will see that it's pretty close, comparable to the physical environment in the virtual plane. You can find the performance brief white paper that we have published showing the comparisons at the above URLs. And the next, Justin will talk about his paper, best practices, and close the session.
Thank you, Ramesh. This is Java in virtual machines on ESX, a best practices paper that I wrote this time 2 years ago and have not changed since that time. So if you're looking at the date on the paper, it'll say January 15th, 2009. It's coming up to its 2nd birthday. I'm planning to refresh it to change the colors on the front page. And then tell my boss, done. Seriously, we'll look at that recommendation about 1 JVM per virtual machine. That'll be the only thing that'll change in this paper over the next couple of months. Maybe I'll stop saying that because everyone is saying to me, sorry, I'm not going to do that. That's the only recommendation there. You can get this at vmware.com/resources/tech-resources1087, or just search for Java best practices on vmware.com. And also have a look at Ramesh's paper here that he mentioned to you, which is also on vmware.com, resources, tech resources. Go to vmware.com and search for performance brief for IBM vSphere. So finally, Java middleware, as you've seen from Ramesh's data, is very viable on VMware. A lot of customers are doing it. It makes complete sense economically. It makes sense from a performance perspective, also, provided you pay attention to the 5 or 6 points that I gave you. Pay attention to those, and you should be fine. Java middleware has undergone extensive testing. Ramesh's test was done 6 months ago. There was a test the previous year, a test the previous year on this stuff. We believe that Java systems can come close to native. If you've got the right application built on the right hardware, built in the right configuration of virtual machine, you can in some cases beat your have your virtual performance beat your physical. And we believe Java applications will be the first applications to go to the web. All the innovation is being done there. Google supports Java. So Java middleware should be tested on virtual machines as a precursor to that move to the web. Thank you very much for your time and attention and for coming so early in the morning. I think we've got a few minutes for questions. Please. Maybe you'd come to the mic and give your question, please, so as we can record it, if you would.
Actually, I have a question. So setting the large memory page size on a VM, is that detrimental to a physical system in any way?
It should not be. The question is setting the large pages flag on physical systems detrimental? You'll get the evidence for physical systems from spec.org or the other benchmarking sites. I think you'll find that -XLP in the IBM JVM case is used in most benchmarking, which says it does not take from the physical performance.
Okay. Thanks.
I speak about virtual performance a lot more. Use it on virtual.
Okay.
Don't even think about physical.
So is it true to say that you haven't seen any substantive difference between middleware products and how well they virtualize? In other words, really no difference between JBoss versus WebLogic?
That's a great question. I don't think I've had that question before. Firstly, we would make no recommendation as to which middleware product you would use, apart from our own middleware product, TC Server, Tomcat Server. Of course, we'd recommend that. But we haven't got the data from exactly the same application under the same load and on the same configuration across 2 different commercial application servers to say one or the other. They both virtualize equally well, in my opinion.
Okay, thank you.
May I take this gentleman next, please, because he came up first. Okay, so just to repeat the question, may I repeat the question? Okay, so losing part of a cluster on the JBoss cluster. Only in the VMware environment. The first thing I would check there would be timekeeping setup and make sure that each member of the cluster is in sync with the time in the same way. That would be the debugging technique I would start there with, and then make sure that you're not in a memory constrained situation on either of the ESX servers on which your cluster is running. That's a very short answer. We would gather ESX top data overnight while this is going on and see what's going on at the VMware layer as a debugging technique. Okay? Oh, we're being thrown out. One more, please.
Do the guidelines change at all when you look at 64-bit versus 32-bit operating systems?
Ramesh can answer this too. 64-bit operating systems are there to give you larger memory spaces if you need larger than 4 gigabyte heap spaces. You're in the big heap space size there. There is some penalty on all systems as a result of the wider words. 64-bit words are wider than 32-bit. The pointers are longer, but it's in the order of 3 to 5% of a performance change between. Every recommendation applies. Yes. Thank you, folks.